Area under and between curves. First day of the last unit. Before we get to area between curves, let's back up and talk about, or remind ourselves about area under a curve. So back up half a step to stuff that we probably know pretty well, and then we'll move forward after that. So this some sort of graph from A to B, and we want the area under the curve. We'll say that graph is f of x. We have something to call it. So what do we do to find the area under a curve? Somebody said it. Antiderivative or integration. So we'll antiderivative of f of x. That gives me the area under the curve, but that's kind of like, that's not enough. What else do I need on that expression there? The limits. I gotta know where to start and where to stop. So I'll go from A to B. Right? That's old news. That's the second part of calculus. The first part of calculus is derivative tells me slope. The second part is antiderivative tells me area. Okay, so that we know. What we're going to do today is the area between these two curves. That should be a g of x right there on that line. Find the area between f of x and g of x. Well, let's see. It looks like, I guess let's shade the area first. Make sure we know what we're talking about here. So there's the area we're talking about. It's going to be some similarities to what we just did. I don't know where that intersection is, so I'll just call it A. And I don't know where this intersection is, so we'll just call that one B. And so that area, so not much space to put it here. Let's do it right here. Area, still an integral from A to B. Any thoughts on what the integrand is? That's the fancy word for what we're taking the antiderivative of. F of x would get me the whole area under f. G of x would get me the area under g. I want to take that whole area and remove the g of area. So what's the best way to remove in math class? Subtract. So f of x minus g of x dx. That's kind of taking the big picture approach to it. The whole area minus the missing area. Another way to think of it, and this will help moving forward next week, is to think of each little piece like we're adding up a bunch of rectangles. F minus g is the height of that rectangle. And the width of that rectangle, it's really, really small. We say that's dx. So we're adding up all the height times width. Like there's a gazillion small little bitty rectangles in there. We're going to add them all up. Height times width, f minus g dx. It's probably easier to think of it the first way, like just the overall total area minus missing area. But next week it'll be better to think of it like this. So I want to show both ways. The sideways one is a little bit weird. So instead of moving from left to right, we're going to move from top to bottom. So we'll still have an A and a B. But those are Y values. And maybe we should put a sample rectangle in here. I want to add up all the rectangles. Let's see. Didn't plan well on the space allotted here. I don't know where to put it. I'm going to try to put it right here. All the rectangles from A to B. Takwa? What's that? You mean if they're left, right, or up, down? Well, they're all of the rectangles. So, like, I just drew one of them, but there's a gazillion of them because they're like infinitely thin, all the way up from A to B. So the height of that rectangle, like you almost have to like turn your head to see it, maybe, if that helps. Turn your paper sideways or your head sideways. The height of that rectangle is the bigger one minus the smaller one. Just like over here we did the top minus the bottom. Here we're going to do the right minus the left. So f of y minus g of y f minus g. And what's the thickness of that rectangle? How are the slices being made? Over here we sliced against the x-axis. Here we're slicing against the y-axis, so it's dy. Most students don't like the dy problems. I guess just because we're so used to dx that it throws us off. But it's kind of the same thing. It's still height times width. It's just things are in y. And the limits are y limits. We went from y equals a to y equals b. So the area between two curves can be written as, here's two different ways to do it. If it's a top-bottom thing, a to b, top equation minus bottom equation dx. That would be if the rectangles are perpendicular to the x-axis. So that was that first picture. From A to B of top minus bottom. Top minus bottom is the height, dx is the thickness, and from A to B is how far we look. We're going to write something pretty similar for the left-right orientation. So from A to B, what's the equivalent on this picture of top minus bottom? What do you think? Because it's this one minus this one. Right minus left. Right equation minus left equation. And the slices, their thickness is dy. You're cutting against the y-axis. So dy if the rectangles are perpendicular to the y-axis. That would be that picture. I guess it's familiarity, but the first one, most students, most people, me included, like that one better. When you get a left-right one, you kind of just have to slow it down, and it feels a little more methodical. Like, all right, which one's on the right, which one's on the left, top to bottom, dy. Like, you really have to slow down on this one. For the top minus bottom, that one, I guess, feels like it makes more sense since we've done a bunch of areas that look like that. Usually that one's a little bit easier to do. Okay, so first one we've done before, kind of. This one is a little bit new, but, turn your head sideways and it's the same thing. All right, some examples. Number one. Find the area of the region bounded by the graphs of y equals x squared plus 2. I guess it would be help if we could identify who's who here. Y equals x squared plus 2. That's the only parabola of the bunch, so that's pretty easy to pick out which one that one is. Y equals negative x. Yep, know what that one is. From x equals negative 1 to x equals 1. So there's the area we're looking for. So usually the first question we ask is this a dx equation or a dy equation? It is going up and down, so like here's my rectangles. So that makes it a dx equation. We're slicing against the x-axis, so this is a dx equation. And usually that's the first thing to consider. Dx.
You always just draw a rectangle and then use that again.
Yeah, that's definitely and I will see that on students' paper. They'll put a little because, and be careful. Sometimes you can do it either way. This one you couldn't do it either direction because you'd have to split up your rectangles right here. The right-left rectangle wouldn't work right there. Also, your equations. This is not always working, but your equations are in terms of x, so it kind of makes sense that this would be an x. Dx equation. While we're on the topic of x's, then let's do our limits. Our limits have to be x limits. So from negative 1 to 1. Thank you. So from negative 1 to 1. And then I need to do top minus bottom. I'm going to show a little extra work that you probably won't show after you've done some of these, but using this format will help when we get to next week. Next week they get a little more complicated, and you won't be able to jump straight to the answer. So putting letters in there will help next week. Maybe not really necessary this week, but it reiterates top minus bottom. So the top is x squared plus 2. And the bottom is negative x dx. All right, I was just looking to see if we're going to use our calculators or not, because we can do that by hand. It's not terrible. X cubed over 3 plus 2x plus x squared over 2. Not awful. But most of the time when we do these problems, like the work is the setup, we will usually use the calculator to get an answer. So grab a calculator. Mine are yours. Math 9. Calculator. Math 9. If you make it to Math 9, you just fill in the blanks. Negative 1 to 1. X squared plus 2. I guess you could even do minus negative x, or you could spare your calculator the trouble and make it plus x. And then let the calculator do the work. .667. So that area that we found is 4.667. Number 2. Find the area of the region bounded by 2 consecutive intersections of the sine and cosine curve. I guess it would be helpful if we remembered which one is which. Let's see, one of these starts at 0 and the other starts at 1. Good. Sine starts at 0. So that would be this one. Cosine starts at 1. So that would be that one. And kind of a weirdly worded question, 2 consecutive intersections. So I guess it doesn't matter which 2 intersections we use as long as they're next to each other. But I would say there's no use using negative ones. Let's use these. So those 2 intersections. There's our area. Maybe we should label these functions even. So that pink one was sine of x, and the orange one was cosine of x. The first question, and probably the most important question, is this a dx problem or a dy problem? Dx. This is a top minus bottom problem. So the integral of something dx. So now I need to figure out, well, kind of maybe get partial credit just by saying top minus bottom. That's the easy part. I can just look at the picture since we labeled it and colored it. I know which one is on top and which one's on bottom. What I don't know is where those intersections occur. So where does the sine of x equal the cosine of x? Unit circle experts? Definitely pi over 4. That would be this first one. And then where else does it happen? What's that? 5 pi over 4. Where they're both negative. So from pi over 4 to 5 pi over 4. Which one is the top equation? For the area that we're looking at, sine is the top one. And that's a little bit tricky because it starts out with cosine as the top one, but in the area we're looking at, sine is the top one. So sine of x minus cosine of x dx. Now we're calculator ready. If you show that much, that means you're ready for the calculator, and you can just give me an answer after that. Math 9. Pi over 4 to 5 pi over 4. Sine of x. Careful with parentheses. Minus cosine of x dx. 2.828. Do you know what would have happened if we had switched? So say we did get it backwards on the top and bottom and we had switched the sine and cosine. Do you know how that would affect my answer? What's that? That's like, yeah, I can see what you're looking at there. That's not what happens, but so if I did cosine minus sine, so say I got them backwards, it ends up being negative. That should be a red flag because areas aren't supposed to be negative. So this is not the thing where, if it's below the axis, it's negative. We're not talking about that. We're talking about actual area should not be negative. So you have a little bit of a built-in check on these, and this happens again next week as well. So make sure you're paying attention to your answer. And I don't want to say if you get a negative answer, just make it positive, because there may be other mistakes you made. But if you can't figure out what the mistake was, maybe just flip the sign and hope that was the mistake you made. Or at least it's a clue that something went wrong if you get a negative. Next week we're doing volume, so it's kind of the same thing. You can't have a negative volume. If you get a negative volume, go figure out what happened.
Why would that be our final answer if you have white spaces like this or areas like that?
Oh, I see what you mean. So it's like, what about that area, and that area, and that area? The trouble is, it didn't, how to phrase this? It did prescribe where we were looking because it says between two consecutive intersections. So, yes, there are other areas, but it only wanted the area between two of the intersections. If you wanted to have all of the intersections, what would the area be?
That times 3.
Yeah, but if you wanted all of them, it would be infinite. It would go on forever. That's why they said, hey, just between two intersections. And then you're right. If you wanted 3 of them, you could multiply by 3. If you wanted 2 of them, so. Number 3. Let S be the region bounded by the graphs of f of x is 3x cubed, g of x is a negative x squared. Find the area of S. How do I know which one is which? It didn't tell me which one. It gave me a picture, which I guess is nice. But how do I know which is which? Now, if you had a calculator, you could graph them and find out. But I think this one's easy enough to figure out who's who. So, Addie, how do you know which one's which?
Or no, the power.
The power. Yes.
3, so there's going to be 2.
Yes.
Well,
For the x cubed, there's going to be 2 hmms. Extrema is the fancy word you're looking for there. Or you can just say, I know what an x cubed looks like. An x cubed looks like that, so that's got to be the x cubed. And I definitely know what a parabola looks like, so that's got to be this one. With a calculator, again, you could graph them both and see, but hopefully you don't have to do that. You can just look at your picture and know which is which. Okay, region S. So that's the area bounded by that. Then this kind of gets to your question on that last one. So this one does have 2 spots to it, or 2 portions of it, but they're not equal, so I won't be able to find one and just multiply by 2. I don't think those are equal areas. If they are, it would be kind of fluky. Let's see. First question is this a dx or a dy problem? Dx. So area is dx, which means I need to go from left to right, but I don't know where those things intersect. So how can I figure out where f and g are equal to each other? That was sort of the answer. How do I figure out where they're equal to each other? Maybe that answer, yeah, where they intersect, we'll set them equal to each other.
But if we're using our calculator, then use our calculator.
And if we're using our calculator, yeah, may as well use our calculator. So I could do that by hand, and maybe that one is easy enough to figure out, but meh. Let's just put them in the calculator and let the calculator do the work. 3x cubed minus x squared minus 10x. And I think I'm going to put them in into y1 and into y2. And I'm going to label it here. That way if I sort of slip up and start using y1 and y2 rather than f and g, I'll be okay, because I've told the grader who's y1 and who's y2. Negative x squared plus 2x. Windows are sometimes tricky, but if you've got a picture, I guess just go with the standard window, see if that works. Yeah, good enough. I suppose if I wanted to make it look like my picture, I could maybe not go so far in the x direction. a little bit better. Okay, so how do you want to find where they intersect? How do we do that? You want to use the calculator, I'm good with that. But how do we get the calculator to find those for us? Do you know where that magic button is? Second calc, intersect, and then be careful, it walks you through what it's asking for. The first curve, yeah, y1, so enter. Second curve, y2. If you've only got two curves in there, it's going to default to y1 and y2, so that's pretty easy. Guess, now I need to pick my spot here. Looks like there's three of them. So one of them's at -2. That one's at 0. But I need to get that far one. Second calc intersect. First curve, second curve, and then go get close to the intersection you want. X equals 2. Okay, so I want the area from -2 to 2. Of top minus bottom. And this is why this problem is on the page as an example. Because what's top minus bottom? Or who's the top? Maybe just ask it that way. Why are you shaking your head, Lexi? There's 2. So thoughts, like it changes. So thoughts on how I'm going to have to find this area? Do 2 separate ones. Because top changes, so I can't just do top minus bottom the whole way. I'm going to have to go -2 to 0 of the pink one minus the orange one. And since they're in my calculator, I'll just call them y1 minus y2 plus 0 to 2 the other way around. Now the orange one minus the pink one. y2 minus y1 dx. Yeah, since who was on top changed, if I just do the whole thing, it's going to count one of these as positive and one of these as negative and add them up, and I'm going to get something maybe close to 0 if those are similar. So instead I've got to separate them and add them up separately. So math 9, -2 to 0. Here's another advantage of putting those in for y1 and y2. I don't have to type out all of that in either spot. I can just put in y1 vars y1 minus vars y2 dx. And if you're a little nervous, you might press enter here and write them both down separately and make sure they're both positive so you know you're doing it right, and then add them together. If you trust what you've done, you can just hit plus and do the next one right after that. Math 9, 0 to 2. y2 minus y1 dx. Let the calculator do all that, and the answer is 24. They are equal to each other. I was not expecting that. But so if you had done them separately, you would find that they're 12 and 12. But you don't have to do that. Alright, so the calculator is super helpful on finding intersections, on actually doing the integration, so you don't have to do it. Helpful in identifying who's on top and who's on bottom if it's not clear. Number 4, let R be the region in the first quadrant bounded above by the, that means it's telling me who's who here. the graph of x equals 4 cosine pi y over 4. That's weird, but it told me that that's the above graph. So I know which one that is. Move my face out of the way here. And below, so I'm going to call that x1 and x2. That's the below graph, is this one. So this first one is 4 cosine pi y over 4, or the rightmost one, maybe is a better way to say that. The left one is 2 minus y squared. Well, if things already feel backwards on this one, why is that? Is this a dx or a dy problem? It's dy. My equations are in y, so this is a dy problem. So again, if it's a dy problem, that means my limits need to be y limits. So from what to what? What are my limits on this one? 0 to 2, because I'm looking at the y things, not 0 to 4. I want the 0 to 2. So 0 to 2. And before I get too involved in the details, if I'm slicing against the y-axis, then this is a right minus left problem. And again, maybe it's overkill to write out right minus left, but maybe it forces you to slow down a little bit and think about which one's the right and which one's the left. This one they were kind enough to tell me who was right and who was left. Okay, so that one feels weird. But now you're ready for the calculator. Math 9, 0 to 2. I'm going to do, since my equation is written in y's, I'm going to put y's in the calculator. But the calculator doesn't know or care if you're using x's or y's. So if you switch all the y's for x's, just because that's easier to hit the x button on the calculator, you can do that. I'm not going to do that on the first one. From here on out, I probably will. 4 cosine, I'll even go fancy with the fraction bar here, pi y over 4 minus parentheses 2 minus y squared dy. So it takes a little extra to find all the to get the y button in there, but 2.426. Again, once you've done a few of those, you're like, wait a minute, the calculator doesn't know if this is an x or a y problem. So why don't I just put x's in there instead? 4 cosine pi x over 4 minus parentheses 2 minus x squared dx. Whoops, not di, dx. And that should be the same answer. So officially it's a y problem, but your calculator doesn't know that, so you can trick your calculator if you think that's easier. All right, number 6. This looks terrible, but it's not nearly as bad as it looks. It's also a very common AP test question, even free response question sometimes. Let R be the region bounded by the graph of y equals e to the x plus x. So presumably they've given me that. And the x-axis from 0 to 2. Okay, so we're talking about this area. That's R. There is a vertical line, x equals b, that divides R into 2 regions of equal area. So somewhere there's a line that divides that area into 2 equal areas. just by looking, can you tell if that line's going to be bigger than 1 or less than 1 or at 1? Bigger than 1, right? Because it's going up, so there's more area, so somewhere in there. So when it comes to drawing a picture, I mean, I can't make it perfect, but it's definitely more than 1. So there's my line, x equals b. I don't know what b is, but it's to the right of 1, and now this right area is equal to the left area. Right, but do not evaluate. That's kind of a new trick, a new statement that we'll see going forward. It means you don't have to do the work. Like, set it up and then walk away. So when you see that, that's good news. Well, it's kind of bad news because it means the problem's probably hard and you can't evaluate it anyway. But set it up and then be done. An equation containing an integral or integrals, which when solved would give the value of b. So this area equals this area. Let's just start with that. A1 equals A2. That's a true enough equation for the problem, but I need some more information in there. I need an expression for A1. Well, that's the integral. It's dx. What are the limits for A1? From what to what? 0 to b. We don't know b, but that's okay. 0 to b. And top minus bottom, although bottom's just 0, so this is just u to the x plus x. If you want to put minus 0 to make it fit the top minus bottom, fine. A2, also a dx problem. What are my limits on A2? From where to where? B to 2. It's the same equation, so e to the x plus x. And now, let's see if that's it. I have an equation. It contains an integral or integrals. So I've got two integrals. When solved, so if we wanted to solve this, we could figure out what b is. Write, but do not evaluate. We like those. Those are frequently on free response questions, and it's, they realize that solving this would take a few minutes, and they don't want you to take a few minutes solving it. They want you to set it up and be good. Yeah, you're right. You don't really know that there's not much of a check on that.
Kind of just like guess and hope.
Guess and hope. Yeah, I hope it's more than that, but I see what you're saying. There's not unless you actually solved it out and then you found the area of A1 and A2, so there would be a way to check it, but that would take a while. All right, today's assignment is worksheet 1.